Okay, why don't we go ahead and get started? Again, from wherever you are, thank you for joining us today for our IWCS webinar series. My name is Dave Cadu, and I am the CEO and Director of IWCS. I'll be your moderator and producer for today's event. A few housekeeping items. Please note that as an attendee, you're part of a larger audience. And during the presentation, all participants will remain in listen-only mode. And as a reminder, this event is being recorded for rebroadcast. We encourage you to submit written questions at any time during the presentation. And we'd like you to use the chat panel on the right of your screen when you joined into the virtual platform for the IWCS webinar. You'll see the chat screen to the right. We'd like you to use that to type in your questions in the space at the bottom and hit the send button. Your questions will be addressed, time permitting, at the end of the presentation. Our IWCS webinar series event is hosted by the Cable and Connectivity Industry Forum. And again, we hope that you'll visit our website and learn more about our 2022 event that's being developed right now for the October conference. So today, we welcome Chris Domenico, who is the president and CTO of MC Communications and Centexi, in Massachusetts, USA. Chris will be presenting his paper on mixing segment specifications for 10 megabit per second single pair multi-drop enhancements. It's a great presentation that was delivered in the 2021 conference and for important application information. Chris Domenico is the president of MC Communications, a telecommunications consulting firm, president and CTO of FiSci LLC, and he's producing high-speed test fixtures. He's also the co-founder of Centexi, developing single-pair Ethernet devices. Chris has over 30 years of experience in the telecommunication industry and plays an active role in the development of a number of telecommunication industry standards. Chris is an active participant and technical contributor in IEEE 802.3, affiliated as a consultant with Panduit Corporation, and most recently participating in the technical and editorial development of 802.3 CD, 802.3 CK, and 802.3 CG, which 10 megabits per second single twisted pair Ethernet task force. And also 802.3 CH, which is the multi-gig automotive Ethernet physical task force. Chris is the liaison officer from IEEE 802.3 to TIA TR42 and is the chair of 802.3.24.2 Internet of Things Vertical Applications Task Force. So Chris, we can't thank you enough for being with us today, and welcome.
Thank you, Dave, and welcome everyone for participating. I've got a lot of words here on these slides. I use these slides basically as informational for those that want more information about the topic. I won't be reading the words. I'll be paraphrasing essentially throughout the presentation. The topic is related to developing enhancements to a project or a standard that's effectively been delivered CG in 2019 for 10 meg operation associated power delivery. The purposes of the enhancements to this particular standard is to add in additional drops to the current specified number of drops they want to do, and those that are driving the project want to enhance this to support up to at least 16 nodes and 50 meter each, as opposed to 8 nodes and 25 meter each. So the project is essentially targeted at enhancing the current existing standard publication, deployment, implementation, and through this effort, models we use to look at the parameterization of the transfer functions associated with the what we call a mixing segment as it relates to insertion loss and return loss. And then the model is further applied to looking at transient analysis and receiver eyes as the metric to assess the constraints of the channel effectively. And so transmitter outputs and receiver eye diagrams are looked at as the process to see if the link segment was sufficiently specified. Just a couple of, well, more than a couple, there's a few acronyms used throughout in terms of the physical layer specifications, as well as connectivity, as referred to as in IEEE speak as the MDI. So this is, as you know it, in terms of base T, modular jacks or optical interfaces are also referred to as MDI and IEEE speak, such as the SC, LC, etc. So this is terminology that will be used throughout to address things that you are all familiar with, which are basically the connectivity, the MDI at the interfaces, and the link segment, which is the cabling portion of it that couples the MDI to the PHY. So you have a physical layer entity, which is the transmitter and receivers, and you have the MDIs, which provide an interface to couple the media to, which are link segments, and in this case, multi-drop or mixing segments that are a little different than the link segment. And I'll show you what that means pictorially. Pictorially, a link segment, and you can see it here diagrammatically represented in terms of the automotive link segment, is the connectivity between the PHYs and the MDI. So the MDI is the interface that couples the cabling, which consists of cable as well as connectors. Here, the T1S, which is a 10 meg, 15 meter reach link segment associated with the 802.3 CG specification, is given to represent what diagrammatically is the definition of a link segment as it relates to this particular PHY. For the purposes of T1S, which is, as I showed you, the point-to-point link, and this is more background, giving you some familiarity with the nomenclature, consists of specifications. In the case of T1S, you have link segment transmission parameters, where the link segment is the cabling portion of the cabling portion that interconnects the transmitters and receivers. Just to digress a bit and to give a little bit more background, I'll use this diagram in that the basis for IEEE's success has been primarily in that the devices, the endpoints, the equipment itself is independent from the cabling as such. People can buy physical devices, PHYs with MDIs, and deploy them in racking configuration or other topologies, and then cabling can be interconnected to these physical devices sometime in the future. They don't need to be tested as systems as such, and therefore they're relatively independent. Somebody can develop, or an equipment manufacturer can produce one PHY, and that can connect to another PHY from another equipment manufacturer. And the way the specifications work is you look into these MDIs, and their electrical characteristics are specified at this point, and the receiver accordingly is specified. So you can qualify a PHY independent from the transmitter, and the link segment as such is also specified independently. So a compliant transmitter can be delivered by one equipment manufacturer. The cabling could be from a variety of suppliers, and the receiver from another equipment manufacturer. And these all could arrive differently at different times and configured in racks and then plugged into at later times. So the specification work as such that the devices themselves are all independently specified with electrical characterizations to allow plug and play compatibility at the interfaces, that if you have a compliant link segment, mixing segment attached to a compliant PHY, then the objective bit error rate can be met. So the basis for these, I would say, independent transmission characteristics, independent from the physical devices themselves, are significant and important in that the users can utilize these specifications to build cable assemblies, link segments, topologies, and test them, and then have devices be attached to them, and they'll meet their objective bit error rate. So here we're, in the case of the mixing segment, we see that the topological considerations are a little bit different in that the nodes are attached as in previous base 2 specifications with coax. Attachments were through AUI and BNC connectors and connecting coaxial cable, but here we're talking about twisted pair in the context of the T1S. So multi-drop has been done before in the past. It's been done in coax and in other projects, but here we're introducing it into twisted pair media. So there's a twisted pair media, which is the mixing segment, which you attach to via these, which you're not seeing the explicit mechanical characteristics of it, but electrically, and well, this is a pictorial representation of that connection, not even a good one, but you get the idea. Stubs are connected to the twisted pair segment, and it's referred to as multi-drop. In terms of the parameterizations, we see here insertion loss, return loss, and mode conversion as the parameters that had been necessarily characterized to support the bit error rate for the multi-drop. And this is a diagram of the point-to-point link segment, which is different. As I shown you earlier, there's no attachments at the in the link segment itself. It's a point-to-point connectivity. And these are the parameters for the T1L point-to-point link segment characteristics. I won't go through these in detail. I'm going to be talking particularly about validation or looking at the validation of the enhancements. The basis for additional nodes or enhancements have been discussed around use cases. And this is a list of those use cases that were articulated for the validation of this particular project. People are interested in it because they wanted to use this CG multi-drop application with powering to do additional, to support other applications beyond which was currently specified. And here you see some representation of those use cases. There were those that were interested for, as an example, industrial cabinet use, you know, with node counts of 40 to 64 with minimum desired length distributions up to 75 meters. So this is the basis for the considerations in the abstract and further work and developments to address the application and support the objective bit error rate. Getting into the modeling itself, the elements of the model to support the analysis was to develop a cable model, as well as elements connecting to the cable, which are effectively these MDI load impedances, which are the input to the at the equipment interfaces. So if you look at where the transmitter is and the MDI in the earlier diagrams, we're talking about attaching these load impedances to the cable, representing the transmitter characteristics as well as the receiver characteristics. So the model consists of a cable and transmitter and receiver loading characterizations, and the load impedance limits are specified in CG and given here in terms of the parameters that were used. As well, the implementation also supports powering as well, power over data lines, and the parasitics associated with the implementation were also included in the transmitters and receivers identified in the characterization of the power over data line, where in particular we would have introduced additional inductances to support the inductances of the Poodle implementation itself as a representation of the parasitics, and they're given in this table. So this is a transmitter model with power over data lines, including the elements of the MDI that I had showed in the previous table, and they're given here in a schematic representation of what was included in the model. And this is a receiver model with the Poodle parasitics. So these are an instantiation of the table values implemented in a characterization of the transmitter and receiver, utilizing those elements of the table. The cable itself, as noted in the project, and the objective is to go much longer distances than were identified in the earlier CG project, where the parametrics associated with the segment itself was consistent with a 23 gauge cable. Here we're looking at extending out to 75 meters or more, and the parameterization here is different in terms of the cable model than was used in the CG products to enable less loss and associated corresponding lengths. And this is a model that was developed in LT Spice, and the inclusion of the Laplace transform to identify the frequency dependence of the transfer functions and phase characteristics were added to represent and match real cable measurements that were made and correlated to using these models, basically. So this is the description of the Laplace function that was used in regard to the cable model. And this is a representation of a 5 centimeter segment, which was used throughout to concatenate and build longer cables with based on these lengths. This is a cable insertion loss correlation to measured and modeled as we've given before, and phase as well. So we were pretty happy with the subsequent output response of the transfer functions using the modeling effect that we had. As I said before, these are a lot of words, and I did abstract them and include them here. I'm not going to be reading the slides, but kept them here for so people could come back and use these as more descriptive text to support the diagrams. But essentially, the building blocks of these segments were added together to concatenate and review the total frequency response of the multi-drop mixing segment using the 5 centimeter increments. And we use the backbone cable or the trunk cable, as well as the stubs were formed from these cable 5 centimeter models. And the basis for the 5 centimeter was to do such, enable the stubs to be formed from the same cabling that was used in the backbone. And the analysis was performed with AC analysis using LT splice. And this Laplace function got us so far in defining our frequency dependent resistance characteristics, but it was not suitable for transient simulations in LT splice. And so in order to overcome this limitation, we used an alternate method to integrate into SPICE, which incorporated filtering characteristics, which enabled the tuning of the frequency response to match the measured cable, and therefore we're able to generate eye diagrams. And both models produce results that closely match. So the cable in both of these analysis frameworks, one which provided transient analysis, and the alternate model, which was done through RC filtering, gave us both a very good match to the cable response. Here is a model comparisons that were used in terms of the parameterization, one with the LT SPICE model and the other with this frequency domain characterization of the DC filter, which was adjusted to integrate into the transmission line characteristics to yield a correct phase response and give a adequate ability to do the transient analysis. And these were the model comparisons given here. In order to support interoperability, which was part of the project, the basis for the considerations for the enhancements were to consider what we were trying to enhance, which is T1S. And so therefore, the basis for the framework for the considerations of the modeling in terms of limitations and constraints used the T1S as the basis to consider the characteristics of the enhancements from. This may change as we get further into the project, but at the point of the presentation of the paper, this was still the framework of which we're looking at as it relates to the operation. This is a multi-drop topology. So part of this topology considerations were to look at the relationships between linear placements of these nodal drops, as well as clumped distributions where you will have nodes at one end collectively adding, which appears as an impedance load, presenting a mismatch to the transmitter receivers at one end of the segment. So there's really two distinct placements of the nodes that we considered. One is this multi-drop even topology, where I'm illustrating that here, where you'll have in-phase addition at some frequencies relative to the interspatial distance, and as these are linearly spaced in distance, they'll add in phase and have a corresponding insertion loss deviations at the suck-out separation relative to approximately half a wavelength. This shows the just kind of a gross approximation of the separation as it relates to the wavelength, and where you have the nodal separations at these particular distances relative to the, as we know, it's not operating at the speed of light. So these have to be factored by the velocity of propagation, as you see here, and then associated with the distance, and then plotted as a half wavelength. And the takeaway really here is just to pick a point is that if you have a 10-meter, separation, you're going to start to see at half wavelengths corresponding to 10 megahertz. You'll have deviations relative to the propagation constant used. And you can see here the corresponding insertion loss deviations relative to these types of tunings, where you see the insertion loss deviations, which are represented as this deviation from, let's say, a fitted function. If the orange curve associated with the limit line were regressed to an approximation, it would correspond somewhat to the link segment specification. But here we have these deviations associated with the link segment distributions. And here we see as corresponds to the earliest slide, a 7.1 meter separation, and these deviations associated with it. So we can create these deviations just about anywhere in terms of their distribution as it relates to the nodal separation. So we know how to space these things. So this is just a mixing segment corresponding to what we refer to as a clump distribution, where you have at the end of 49.4 meters clump of nodes associated with the near end, which is 60 centimeters separation of nodes, separated then by a long cable with these clump nodes. And what happens is that you get similar results. You'll get a phase relationship between the clumps at both ends of the impedances. But the difference here is that versus the linear separation is these clumps appear as will reduce the 100 ohm impedance, or effectively the 50 ohm impedance. It impacts the termination impedance in such a way that you have a mismatch between two ends of the cabling associated by a wavelength that is related to that separation, and as it relates to these clump nodes deviations. So we had to explore both the linear distributions as well as what we're referring to as these clump distributions, which effectively lower the mixing segment termination impedance, and therefore will create these patterns as well, but at wavelengths associated with the distribution distances. This is a rather busy slide, but various topologies were constructed and related to a metric considered. It's a level below, looking at these mixing segment distributions and trying to assess the corresponding issues with a receiver sampling these transmitter output waveforms over this particular transfer function. So the eye diagram gives you a way to assess the issues with these suckouts relative to the receive eye, and allow a metric to correspond. I apologize for my dog barking in the background. So in any case, I love dogs, so we will have to put up with him for the period in which he chases the postman for a few minutes. Any case, so we needed a way to assess the impacts of these suckouts, as you see here, as it relates to the distribution. Now, there's other ways to do this in terms of continuing on with looking at transfer functions. We can look at insertion loss deviations. We can look at time domain analyses. But here we're looking at the receive eye as a metric to look at the impacts of some of these distribution suckouts created by these topologies. So this clump distribution was evaluated as a particular worst case, quote unquote, where the clump configurations are given here and their separations and drop lengths, etc. And, variety of these distributions were reviewed. And this one in particular had a correspondingly worse reflection corresponding to the bandwidths of interest as it relates to the eye diagrams. So utilizing all of the models and the transmitted characteristics and the model considerations related to distributions of nodes consisting of both linear and what we're referring to as this clump distribution, eye diagrams were generated to consider as the metrics or the means to look at the results of these mismatches. And various lengths were constructed and corresponding eye diagrams were generated using the analysis. And you see here the left and right diagrams are associated with what I'm referring to as these power over data line parasitics. So the left side has the power over data line parasitics and the corresponding eye diagram. Its length is 13.6 meters. These stub lengths are 20 centimeters, and it's 2 times because you're going up and down, and the total channel length is 30 meters. So this is the consequence of the model relating to the cable model plus the transmitter plus the receiver, all integrated together and producing these eye diagrams over those topologies that we reviewed in terms of the linear distributions as well as the clump distributions. This is 40 meters, and you can see from the subsequent slide that we're degrading the eye as we grow the topology somewhat in some cases. Some of these have a non-intuitive consequence in that some of the interference patterns associated with less losses are actually more pronounced. As you know, the return loss is a function with the power that appears back at a transmitter is subjected to the losses. So the return loss effectively scales as the round trip insertion loss. And so that in some cases, the shorter segments corresponding to less loss between participating nodes actually will create eye patterns that have more severe closure due to the reflections associated with the interference of the position of the transmitter and receiver corresponding to its loss. So the loss between the elements of the nodes also contributes to the eye closure. Just as an example. So actually some of these may be non-intuitive in that case, but describe the circumstance. What appears is that the poodle parasitics on the right become the dominant factor in the clump distributions without poodle. In some cases, because of the longer lengths and the associated losses between it, are impacting the eye closure. But the poodle parasitics will dominate in terms of the inductance, and you see that on the right with the poodle impedances. And this is 50 meters, again, with and without the poodle parasitics and the eye closures. And this is 60 meters associated eye diagrams. And this is 70 meters with poodle impedances and without. Now, during the course of this project and the the basis for a paper, which I'll be providing IWCS an abstract on, and I didn't get time to include those slides, but over the course of the project, we've actually developed a means to compensate for these nodes using tuning out and compensating for these inductances, and are able to restore eyes that you see here, which will be covered in the subsequent paper developed on this topic. So at the time this was presented, this was the result of the eyes and their closures, and subsequently we have developed means to compensate these eyes and restore the eyes, where effectively you're looking at cable loss essentially, and that these parasitics that you see here and observe here have been compensated for. And effectively what the results are now is that you're limited by the cable loss essentially, and these reflections that we had observed due to these parasitics up to some point. At some point, the poodle inductances take over, and you get droop, which is you're not able to compensate for. So as I said, that's kind of like, this is a precursor to more work that was done that will show that we can actually open these eyes up. So at the time we concluded this, we were looking at these eye closures and concerned about the viability of actually achieving these use cases that we had shown earlier in this table. But as we had further explored this, we have been able to recover these eyes by introducing other circuits that would compensate for the parasitics associated with these impedance imbalances, these capacitive, primarily capacitive, until the poodle inductance takes over by tuning these with inductors. So there's a follow-on to this. I didn't try to be so ambitious to do all of that and wanted to stick to this abstract. But the good news is that it looks like we'll be able to do, generally speaking, up to, I'm reasonably confident that we'll be able to achieve these 75 meter, at least 40 node distribution solutions for the enhancements. Questions?
Okay, Chris, thank you very much for delivering that very interesting paper. Obviously, very fundamental technologies to these various applications. If anyone has any questions, please be sure to enter those into the chat box on the webinar platform, and we'll present them to Chris accordingly. And Chris, we are all dog friends, so not to worry about your dog. I hope the postman survived.
Yeah, I have no control over my dog or my wife, so either one are uncontrollable entities, you know. So.
Yeah, none of us really do. Anyway, I noticed that you're talking about 50 and 75 meter evaluations, but are single pair cables also being assessed and modeled using the conventional 100 meter lengths, or are these segments measured to specific application lengths?
So corresponding to projects in IEEE, there are TIA specifications evolving in support of these topologies. So they're not completed yet, but they're working on rationalizing these lengths and how it relates to current telecommunication design practices, to have corresponding distances related to telecommunications designs. Now, as I present these here, these are IEEE centric specifications related to particular environments such as automotive and in industrial. There is a TIA spec evolving on single pair addressing 1,000 meters, as well as shorter distances to be determined. Target topologies are longer than 100 meters at this point, but we're talking about also a family of specifications, including higher data rates. So single pair now is being considered for beyond 10 meg as well. So there'll be a variety of data rates and media specified for a broad range of applications for current and developing telecommunication infrastructures.
Great. That makes sense. And perhaps, you know, again, looking at lengths being the issue, with increasing power being applied to devices over single pair, are you seeing any correlation to increased bit error rates or other data transmission degradation?
Yeah, the powering aspects related to, you know, you're talking about low bandwidth versus higher bandwidth. So unless the powering itself has associated transients relative to its operation, which, you know, we're pretty well understood and controlled, they're reasonably well isolated from the quote unquote from the data portion of it. So power and data do coexist with, you know, with reasonable confidence. As we all know, PoE is quite successful and people have been dealing with this for quite some time. So the power and data is something we've been implementing for a period of time. Now the issue, as you probably know, and, you know, not to dig up dead bodies, but the characteristics of the thermal considerations have been the primary constraint on coexistence of powering and data. Basically, it's been more on temperature rise and effects of thermal heating rather than any operational powering data concern.
Excuse me?
Yeah, it looks like this. I had a double click now. Am I back? Can I see you? Can you hear me?
Chris, this is Becky from IWCS. I think Dave may have gotten frozen. It looks like his screen share and his video is frozen right now.
Okay. So that it's not me driving this issue, right?
No, it's not you. But actually, I don't see any more questions that have come in yet. Oh, Dave's back. Hey, Dave, I'll let you take back over.
Thank you. I apologize. I'm not sure what happened there. Just probably internet failures. Anyway, again, please note the contact points that I'm showing here for Chris if you have any specific questions that you want to address with him offline. Also, I want to remind you that for our upcoming IWCS conference in October, we're receiving abstracts now. So if you'd like to present your work at IWCS, please go to our website, and easy process of online abstract submittals so that you can be included in our program. Each of these IWCS webinar series presentation events are recorded. They'll be archived on our IWCS.org website. Normally takes up to a week or so to get these posted. The webinar series will conduct technical paper presentation webinars as well as sponsored company events several times each month. Our next technical paper presentation webinar event will be on Friday, April 15th at 10:30 a.m. Eastern USA time. And each of you will be receiving an announcement for the event. Please feel free to share these with your colleagues so that they can join and register as well. So Becky, any last minute questions that you might see?
I do not see any last minute questions, Dave.
Okay,
Yeah,
thanks.
Dave, I forgot to mention the participants in the paper were Bob Bloss and Paul Wachtel from Panduit, without which I would not have been able to complete this work. Both had contributed significantly, and I failed to mention them in the beginning, but hopefully, mentioning them now, I know some have left, but so I feel a little bit bad about it, but anyways.
Yeah, no, I appreciate that. And Panduit is a strong contributor to IWCS as well. So thank you to them. I do want to recognize and thank our IWCS partner sponsors who contribute greatly to the success of the Cable and Connectivity Industry Forum. Without their strong leadership and generosity, we would not be able to bring these important technical innovations and information to you and our global community. So again, thank you to these leading industry suppliers, and thank you for your support. Again, just to remind you that for over 70 years, IWCS and the Cable and Connectivity Industry Forum has been the recognized leader in showcasing these new technologies and cable and connectivity products, processes, and applications. With perseverance and confidence, the IWCS Cable and Connectivity Industry Forum will now take place live on Monday through Thursday, October 10th through the 13th in 2022 at the Rhode Island Convention Center in Providence, Rhode Island, USA. Please watch your inbox, social media, and our website to learn more as the exciting information becomes available. We can't wait to be back together again in person after these two very, very difficult years. So please visit our website at iwcs.org for more event details. So again, thanks to Chris and thanks to all of you for participating in today's event. And that concludes today's webinar. Have a great weekend, everyone.